Good morning, all. Today I'm going to talk about the game theory, which is in fact a very important topic in the microeconomics lecture. So let me come to the game theory lecture. So we know that in our real world, in life encounter, there's so many games in which we are all being part of. So it can be a chess game, it can be football, cricket, or it can be matching pennies, or many other games which all of us play, badminton, football, everything. These are called social games. But at the same time, there are also individual games, and as well as people do interact. So all this can becomes or brought under the framework of game theory. So game theory models strategic behavior by agent who understand that their action affect the action of other agents. Therefore, this is very pertinent to understand what is theory altogether. So, what is a game in that sense? A game is being played whenever people interact with each other. So, bidding in an auction, pricing a commodity in any platform or online platform or offline market, uh, then adoption of new standards, then the crisis management, etc., comes under the very understanding of game. So the most important point in which one has to keep in mind regarding the games are the strategic the behavior or the strategic behavior are interdependence, and the interdependence is the most important element as far as the game theory is concerned. And this is in fact have a departure in point from what we have learned till now about microeconomics, where you don't actually too much consider this interdependency element inside your behavioral formation, especially rationalizing the rational attitude of an individual economic man in that sense, or woman. So, interdependence is a very important and crucial element as far as the game theory is concerned. So, one person's behavior affect another person's well-being is what is called the interdependence addresses on. So, what is not a game is actually one person playing a thing by himself, such as Monopoly. See, in the Monopoly, what is actually the problem with Monopoly is that only one seller. So there is no interaction between sellers. So, or the behavior of the sellers is not being basically influenced by the seller, because there is no other seller exists literally. So in that context, a seller context, this monopoly seems to be pretty awkward to classify it as a game. So similarly, you also have an infinite interactive sellers game like perfect competition, where you know that infinite number of sellers. So what is the problem with this thing? So you once the game premise is infinite, then equilibrium or the best solution, finding a solution to that particular interactive mechanism is very difficult in that sense. So where you fix, of course you can say that you can fix the price a priori, but where is the quantity, and can anyone fix the quantity? So one, you have only price being fixed with no quantity being fixed. Therefore, you cannot say that there is an equilibrium or there is a balance. So that only one price we have actually an infinite kind of quantity, that is, or one quantity. It is actually synonym to the balance in that sense. So it is a little tricky understanding in that context, that is, these are not games at all. I preferably speak that when under perfect competition, if what is the perfect competition, a and a clone has the same information and ability, agility, whatever. So then only you can see that A clone is actually equal to A. So in that sense, whatever competition which you make between these two, a priori to the competition, you can say that, or this is the result, because they are unbeatable each other. So this is what is called a clone. So if you know perfect information, as Solomon said, he knows that I know that what you know, and you know that what I know, is what is called the symmetry of information, which is perfectly applicable under the premise of a perfect competition. Then interestingly, you a priori know that what is actually the response of the other person and yours by the other person. So in that sense, your strategies are actually not alien to the other person. He or she knows what is your strategy, and you know their strategy too. So therefore, in fact, the result of any of that kind of situation is bizarre. So we don't actually therefore really go into the details of all this thing. So let me come to the problem directly, which faces the game theoretical framework. There are three major tensions of a strategic interaction, basically follows in the game theory. And game theory, as we know, that a theory of strategic interaction is always goes with the conflict of interest as well as the cooperative interest. So two type of interest basically, or strategic interaction basically, uh, you know uh, will take place under the game theoretical framework, which is in a simple sense is the non-cooperative games and the cooperative game kind of thing. So in the non-cooperative thing, normally, as we know, that conflict of interest is always the case, and in the cooperative game it is not the case. It is actually joint actions, in fact, optimize the social well-being in that sense. So uh, the tension, the real tension which we spoke about, is the three major tensions, like conflict between individual group interest and group interest, strategic uncertainty, insufficient coordination. So let me come to all this thing later when we discuss about this thing. So before that, let us come to the game theory as a history. So we know that in economics, game theory is widely these days applied, especially in the aftermath of the mid 20th century, or the early World War, or later of the World War. But of course, the application of the game theory was started much before. Like we know that the duopoly model of Cournot, in fact, talked about the equilibrium of the duopoly interaction, two firm interaction. Uh, in that 1838 paper on this particular aspect, or book on this particular aspect, in fact, talked very extensively about all this aspect. So Edgeworth also applied this game theoretic framework in early 1881. He published, and that is also deal with the interactive framework, especially the game framework. But only in 20th century, especially 1930, by the work of Sermilio, he tried to prove, or he tried to demonstrate the fact that chess-like games, which is normally we believe that an infinite move game, uh, even chess-like games can be solved in a large finite number of moves. So finite number of moves, but how finite it is, we don't know. But Sermilio had theoretically proved that chess-like games even have a solution in that sense. But after that, in a couple of, especially the post-war scenario in the United States, two gentlemen like stalwart. In fact, von Neumann and Morgenstein wrote the theory of games in the book in 1944, where they extensively used this framework, and that is how it was get popularized among the economists, especially the mathematical economists of that time, engineers and other social the natural scientists who basically started learning and doing modeling in the economic analysis of that time. So especially in the United States in the early time, but later, or contemporary times of that, the theory of games by von Neumann and Morgenstein, Nash uh, had developed a kind of, in fact, he challenged the existing notion of individual optimality leads social optimality philosophically, and he questioned the very principle of Adam Smith's understanding of the same. Uh, and he developed individual utility maximization leads to the social suboptimality. So this suboptimality condition is also an equilibrium. So this is what is in a simple sense we normally speak as Nash equilibrium, which are trying to exhibit us a lot of insight into the understanding of or application of the game theory into economic analysis. So we will discuss that later. But after Nash, Harsanyi, Selten, and many people, as I said, Oman, Schelling, so many people had worked really on the non-cooperative as well as the cooperative game frameworks. In 1994, as a token of appreciation, the Nobel Committee or the Sveriges Bank of Sweden, in fact, offered a Nobel Prize for these three guys, that Nash, Harsanyi, and Selten, which again popularized the application of game theory in economics. Later, Oman and Schelling in 2005 again received Nobel Prize for game theoretic analysis of conflict and cooperation. So these two Nobel Prize comes with the two different strand of literature, in fact, or two different strategies, as we had rightly pointed, that the cooperative and the non-cooperative behavior, basically, that is what has been addressed in these two Nobel Prize, or by this Nobel Prize. But later there are many people had worked on this areas. We are not going to the details. So now economics is very widely used in this aspect. Now, as a note to my listeners, my students, you can also refer my 10 lectures on game theory, which is basically preliminary lectures on game theory for undergraduate students. So if you are new in game theory, you can listen that lectures very well. Short lectures, which is concise, and short lectures, especially, it is largely descriptive kind. But what we do in this lecture is a little higher than what we have done for the undergraduate. So we introduce many Payoff Matrix and different kinds of game analysis here. So if you want to really go into the basics, then definitely you have to go through that kind of lectures also. So it is also available in my YouTube channel, so you can browse. Now the non-cooperative versus cooperative game is the starting point, as I said earlier. That is in the Nash equilibrium, and this thing where, in fact, developed the setting of non-cooperative game theoretical framework. Uh, and later there are many, again, human interaction and many cooperative behavior also. So the in that context only we have the cooperative games, especially Schelling's work is very, very classy in that. So, a non-cooperative game theory in which individual decision making, group decision making, specify procedures leading individual decision to group outcomes. So, this is what is actually the kind. And then the solution concept, prescriptions, and predictions about the outcome of games, etc., are discussed in this aspect of game theory. And then in the in the cooperative game, a model joint action is always been discussed. That is, how we optimize the social well-being or even individual well-being in a cooperative sense, as well as in the non-cooperative case, uh, as we have pointed elsewhere. So, some of the application of game theory we need to basically talk. The study of oligopolies industry containing only a few firms, or the study of cartel such as OPEC, ASEAN, all trade blocks, etc. The study of externality using economic common resource such as fishery and other things, the study of military strategy, etc. All can be brought under this framework of a game theory. Now, that is the beauty of this particular application, or kind of a method. So, what is a game in that sense? A game consists of a set of players, a set of strategies for each player, the payoff to each player for every possible list of strategy choices by the player. So, this is what is called the payoffs. And so three things are very important as far as the game framework is concerned. So that is, there should be players, there should be strategies and payoffs. A game with just two player is a two player game, whereas if it is an n player, then you call it as an n player game. So one person, we have already said that there is no game for one person. So so minimum number of players should be two. So that is what is the basic model is always a two-player game model. So we will study only games in which there are two players, each of whom can choose between only two strategies. So an example of two-player game is the following. That is, the players are called A and B. Player A has two strategies called up and down. Player B has two strategies called left and right. So now it is clear that two players, they have two strategies each. Oh, the first player has an up and down strategy, the second player has left and right strategy. So the table, which is actually comprises of different moves of these two players with their respective strategy, is forms as a payoff matrix. So both player for each of the four possible strategy combination is therefore comes under the payoff matrix. So a payoff matrix simply looks like this: B on player B on up and player A on left. You can change, you can transpose, no problem. So the result would be in fact same. So this is what is actually the beauty of this particular understanding. Now you have a left and right for player B, up and down for player A. Now in that sense, this the first the column which is shows actually A's behavior, and the second column is always follows the B's behavior in this case. So this is the game's payoff matrix, and player A's payoff is shown first, player B's payoff second. So simple. In order to understand it clearly, you can look into the color of it. So ace is up and down, so this pink color is used to depict this particular thing. So the green is actually the other second player, right and left, so that is being shown in green. So A's payoff is 1 and B's payoff is 8 in the column which is we have colored, other than the yellow color. So again, it's the same. If A plays down and B plays right, then A's payoff is 2 and B's payoff is 1. So in the first case, A's payoff is 1 and B's payoff is 8. So remember this, a play of game. A play of game is a pair of such u up and right, where the first element is the strategy chosen by player A, and second is strategy chosen by player B. So what plays are we likely to see for this game? So this is a very important question. Now if it is you are a likely play is a question, then answer is, if B plays right, then A's best replay is down, since this improves A's payoff from 1 to 2. So UR is not a likely play. So that is what is actually the first conclusion. So the second you know column, if you, or row, if you examine, that is this DR, or that is down and right, a likely play. The answer is, if B plays right, then A's best replay is down. So it is a, if A plays down, then B's best replay is right. So DR is likely a play in this case. So we have checked two column, two payoff matrix, two boxes in the payoff matrix. First one 1 and 8, second one 2 and 1, where we examined that whether 1 and 8 is a likely play when compared to 2 and 1, and we came to a conclusion that 1 and 8 is not a likely play, because there is always a chance of improving for the other if the person is playing in this case. Therefore you will always move towards the other one. But at the same time, when we examine this 2-1 example, where we found out that that is a possible solution in the again, if we want to extend the other boxes in the payoff matrix, if we can ask the same question, is the down and left a likely play? If A plays down, then B's best replay is right. So DL is not a likely play in that sense. There, and similarly, if you up and left is a likely play, is the question. If we move, then if A plays up, then B's best replay is left itself. So if B plays left, then A's best replay is also up. So up and left is a likely play. So we have found out that two likely plays and two non-likely plays. So 3-9 and 2-1 are likely plays, and 1-8 and 0-0 is non-likely. Therefore, a play of game where each strategy is best replayed to the other is a Nash equilibrium. We immediately came out with a conclusion that if it is a finite game, as this payoff matrix shows, you have only 4 moves. So in that sense, 4 strategies, in a combination of 4 strategy, therefore you have at least one equilibrium. So in the paper, Nash in 1951 paper, especially the 2% game paper, he demonstrated that any finite, one of his theorem is any finite game is always have a solution. So it is only finite games as solution. So if it is an infinite game, no solution. So that is the corollary which one can basically derive out of the paper, which is one of the best papers of the time. Especially the application of the paper in economic analysis and microeconomics is enormous. So this is in fact incorporated into our own understanding in that sense. A play of, therefore, a Nash equilibrium is an equilibrium, as I said in the beginning, that it is also a suboptimality. Because of the best strategy you choose, you end up at a suboptimality. Basically, the Nash equilibrium is not actually them. It is the result, the best result out of the best strategies, but it is not actually individually, not necessarily individually best. So this is what is actually the philosophy which he was challenged and made gave a proof. So our example has two Nash equilibria in that sense. As I said, your 3 9 and 2 8 2 1 is two Nash equilibria here, that is up and left and down and right. So if that is the case, then UL and DR are both Nash equilibrium for the game in this payoff matrix. Then UL and DR are both Nash equilibria for the game, but which will we see? Notice that UL is preferred to DR by both players. Must we then see UL only? This is another kind of questions which we have to address. I will come to this point later. So let us move another sort of a game uh, and payoff matrix, which is a very common game exhibition, what you call illustration in textbooks, or demonstration in textbooks. This is what is called the Pressness Dilemma. So what is the Pressness? To see if Pareto preferred outcome must be what we see in play of a game. Consider a famous second example of two-player game called the Pressness Dilemma. As I said, what is this particular game? It is the possibility of confession vis-a-vis silence of the convicts. So maybe two people are at wrong place at wrong time or whatever, but somehow the sheriff or the officer find that they have involvement in crime. So if that is the case, then how do they behave is going to form as a payoff matrix here. So two convicts in this case, I don't basically call them convicts, suspects basically. So two suspects, Clyde and Bonnie. Now they have two strategies. Clyde can also be silent as well as confess. If Bonnie too have that option, then he can be silent or confess. Now if he silent means he say that he has no role. If confession means he say that he is having a role or she is having a role. So if that is the case, then you have a payoff matrix follows like this. Silence gives you 5 years imprisonment each. Okay, so the option is given to you. Now if one person confess, the other is being silent, then the silent person is actually given more basically more imprisonment, in this case 30 years of imprisonment, and the confessor may get perhaps 1 year, because he said the other person is in fact involved in the crime. So this is follows the other person also. Now if both confesses, then both had involvement, and they will be sent a jail which is greater than the silence example. So what plays are we likely to see for this game in that context is a question. Suppose if one person, Bonnie is silent and Clyde confess. What happens? Bonnie is playing silence, then Clyde's best he plays confess. Okay. Now if Bonnie play confess, then Clyde's best replays also confess. See, if Bonnie plays confess, then Clyde's best replays actually confess. Now, so no matter what Bonnie plays, Clyde's best replay is always confess, because otherwise confess is a dominant strategy in this particular case. See, look at this. So if the people are actually being silent, uh, they want to, then but that never happened, they are silent because of the uh, selfish interest of them, or because of the non-cooperative, basically because of the setting itself. uh, you know the other person has, if you don't confess, then the other person, you don't know that the other person is going to be a silent or choose silent or confess. If you confess, then uh, if the other person becomes silent, then you have all the probability of getting 1 year imprisonment at the least, or at most you will get an imprisonment of 10 years. All right, so the other person also thinks in the similar line, and you end up with a strategy which is both get confess, and both will be sent jail, 10 years of imprisonment than both being silent. So this is what is called a dominant strategy of this particular game. Now, sorry. Similarly, no matter what place Bonnie is best replays always confess. Confess is a dominant strategy. Bonnie also. So the only Nash equilibrium for this particular game, so the up and down game, what we have had is actually two equilibria. In this Pressness Dilemma, we have only one equilibrium. This is having only one equilibrium. That equilibrium is itself is a dominant strategy followed. The Nash equilibrium is inefficient. As we know, the only Nash equilibrium is inefficient. As we know, the efficient one has actually been silent, but the inefficient result is the product of this particular behavior of an individual. So it is quite clear, as in the beginning I said, Nash try to exhibit a fact that even you are making your best strategy, what you are ending up with, you are ending up with the not that best thing. Your expectation that you will get only 1 year imprisonment, but you end up with 10 years imprisonment. If you are silent, your expectation you will become 30 years in prison. If the other person is actually confess, so you have this threat of confessing by the other person, so therefore you confess and the other person also confess. So if they confess, then definitely both of them confess and get an inefficient result. So now we can also look into other games such as matching pennies game. Simple, this is what is called a zero sum game. Why it is a zero sum game? As we said, as this particular game sounds, that is matching penny says that your gain is my lost money, or whatever you gain is actually a thing which I am losing. So in that sense, this game is a very interesting game, and it's called the zero sum game. So if 1 and 2 has strategies, the head and tail. So if head comes, then the other person gets, that person gets things from this person. So ultimately one's gain is the other person's loss in that sense. So if you match, zero sum is actually the result of this game. Now there are other games such as coordination games. In that game, see, if you coordinate, you work in a coordinated fashion, then only you will get result. For example, if both place a strategy of AA, then they will get some benefit. If both plays BB, they get benefit, otherwise they don't get anything. So a coordination want to use the same strategy, AA or BB. Example, traffic rule. So it is an interesting thing. See, what is the traffic rule always say? So if there is a red light, you have to stop. So a red light means a coordination. It is demanding a coordination. Be stopped, and you have to stop there. Then only you get benefit. Otherwise, you don't get benefit. If in the red light you drive, then there is always a chance of losing your life or whatever, meet an accident or whatever. So this is what is called a coordination game. So if a green light means you cannot stop, you have to pass. Then otherwise again it will cause ruckus in the system. So this is what is called a coordination game. It's all about classic game of Pareto coordination. Is a coordination want to select the same strategy prefer to coordinate it on A rather than on B. So then you have this particular thing. Then you have battle of sexes example, like a couple wanted to go or lovers wanted to go to movie or opera or whatever, but they may be having slightly different preferences also. For example, one likes opera, the other may be liking more movies. Okay, one person want to go opera and the other person goes movie, then there is no love. Okay, if they go together, then only there is some meaning for this particular thing. Otherwise it is an individual, there is no game. Okay, so if it is a game and interaction between the two things, we have to talk about that. So if one person goes for movie, as I said, the other person goes opera, then collectively they don't gain anything. So individually maybe, I don't know, because that is not actually our concern in this case. So if it is lovers, their utility is joined. Okay, so if one person likes opera and the other person likes movie, then there is an issue that the person who love opera gets more utility if you go for opera case. Movie the other person gets. So this is what is actually this game try to say. So coordination game want to go to an event together with slightly different preferences. That's it. Then you also have other set of games such as hot dog or chicken game. In that it's an interesting one. Coordination, again it's a coordination game but a negative sense. So want to take different strategies. So for example, in the chicken, if you want to drive, there are many part of the world. Okay, we can start an Indian example, Kerala example. Earlier there was Mamangam. So Mamangam is actually kind of an act which is actually sending this fief lords or the warlords against their army or their buddies against the ruler who in fact you know conquered their land. So Samudri is actually the ruler. So this Mamangam, this people, warriors used to visit the place once in 12 years, and it's a kind of a chicken game. If you are at the age, then you will be sent, and you have to go. So your strategy is to go and fight and die, or kill the Samori. So why? Because that is a chicken game also. It is also called a chicken game. Your strategies. Now this person is actually sent at the time. This person should not reach this particular thing. If that is the case, then they used to send people to kill this. So in Sicily, also there are chicken games. There are many places. This youngsters used to play chicken games. So if one simple bridge, then they have to cross at the same time. If both the person drives to the bridge, then both collides and dies. Okay. If one refrain from doing that, then that refrain person is called chicken, or the other person is called actually this hawk. Okay, so either the way, these are called coordination games. Okay, so there are different meaning for this thing. In this example you have hawk, then both drives means hawk means both drives. then what happens is that the result is death, or they lose their life. So one person play hawk and the other person play chicken. That is, the person tried to drive but found out that the other is driving simultaneously. Then this person who stopped or didn't drive is a chicken. So he in fact or she in fact saves his or her life, but called chicken. So their utility would be lesser, but at the same time the person who acted hawk uh, gets better utility because he played at the same time he saved his life. So better double dhamaka in that sense. Again, this can be the other way around, and if both play chicken, didn't both in fact relatively not worse off in that sense. So again, this is also a coordination game. So you have different equilibrium. Then you have pigs, games of pigs, dominant pig and submissive pigs examples, and there are so many games in fact is out. So now the question is that who plays when? In both example, the player choose their strategy simultaneously. This is what is called as simultaneous play game or simultaneous strategy. Such games are simultaneous games. Okay. Now, but there are games in which one player plays before the other player. Such games are called the sequential uh, play game. So the players who plays first is the leader and the player who plays second is follower. So now who plays when is itself demarcate the characteristics of game, which is as we said, the simultaneous game vis-a-vis the sequential game. So there are two type of games, sequential games and simultaneous game, as we said earlier that the cooperative non-cooperative game kind is also one kind of a strategy. Cooperate or you don't cooperate. So now we will discuss this thing, the sequential versus the um, uh, you know the other one, simultaneous game in the next lecture, because we have to move a long way to discuss all these things. So thank you so much for listening my lecture. So let me stop it. Thank you.